Solving logarithmic equations is going to require two new rules to be able to set up and solve our equations. So the two types, or the two rules that you're going to be working with. All right. The first type looks like this. You have the log of a base that results in the value of y equal to a number. And so notice that you have only one logarithm written. So there's only one log, and we have looked at simplifying down what this logarithm is. And so on this side, what you're going to want to do is you're going to have your strategy of turn into exponential form. All right. And so once you turn this logarithm into exponential form, it's going to give us another strategy to solve. So your first job is to say this base to some power equals this value. Right? And now we can use some older strategies or techniques, because now what we have is we have an exponential equation, and we've looked at those before. All right? So your strategies for being able to solve this, there's two different types of strategies. The first strategy when you're solving these type are if you can create like bases, then the powers must be equal. So if if you can make b and y like bases, right, then we have a strategy for that. And that strategy would be that using that old rule that a to the x equals a to the y, meaning I can set my exponents equal to each other and solve. Right? And so this is one type of strategy. Right? Now, if you cannot make your bases the same, that's the other kind of type that we have to worry about. All right? So if you cannot make b and y like bases. Okay. Then we had another strategy for that, which was using ln. So in that case, when you have b to the x equals y, our strategy is going to be to take the ln of both sides. Okay. And that again allows our exponent to move out front as a factor. Okay. And then we can solve. And so now this is where using our calculator really came into play last time. All right. Now, so the other things that you'll have to notice, or you'll have to know about these types, is we have what's called a domain issue, where this value, all right, your result, must be greater than 0. All right, and so again, that's what we call a domain issue, or a restriction. All right, so you have a restriction, and that is that y must be greater than 0. So you're not allowed to get 0 as a result, and you're not allowed to get negative numbers as a result. And so this is going to be important, because you now will need to do some checking to be sure that the final answer that you come up with in some of these values, that this is not a negative value. All right? So for example, if I have some of these cases, I don't necessarily have to do this strategy. Sometimes you're going to get the b and the x values to be known to you. And so there's another type of strategy that we'll talk about. All right? So that's the first type. All right? Now your second type, all right, is going to require to use your rules of logarithms to condense. Right, so let me shift this up. Right. Now, in your second type, your goal, right, is to use the rules of logs to condense. Right. And once you condense, you're trying to make an equation with two different logarithms, one on each side. So log base b of some value is equal to the log base b of another value. All right, and so this is another common type. So this is very similar to the exponential one actually here. All right, is that if we have the log of a base with a result, the log of the same base with another result, that the only way these two could be equal to each other is if our results can be set equal to each other. Now again, you also have restrictions on this as well. All right, so in your restriction, you must make sure that the value in both logarithms is greater than 0. All right, so again, you're not allowed to have any negatives or even 0 in this case. So again, there's always going to be some kind of changes to these or other rules where, you know, there's other options, but these are the kind of the other main two types that we haven't really worked with yet. So we're going to do a couple of examples and see how these are going to work together. All right, let's zoom in here a little bit. All right, so let's look at example number 1. All right. So for example number 1, what I have is I have a -2 log base 5 that's going to result in a 7x equal to 2. And now to use this, this is the first type that we were looking at that I just showed you. There's only one logarithm. Now the issue is that you can't solve until you get rid of anything that's being added, subtracted, multiplied, or divided. So the first thing that you need to do is to undo this operation by dividing. And when you divide, right, you are only affecting the values on the outside of the logarithm. You are not allowed to touch the logarithm or its result in any way when you do this division. All right? And you also need to make sure that you divide by the negative if that's attached. So now what you're going to have is the log base 5 of 7x equals a -1. And now we can use our exponential notation for this. So 5 to the -1 power equals 7x. Again, that's changing this log into exponential form. And this 5 to the -1 power, again, a negative exponent means the base is on the wrong side of the fraction bar. So this is really 1/5 is equal to 7x. And to undo this multiplication, instead of dividing and having complex fractions, I'm going to multiply by the reciprocal. So as long as I do the same thing to both sides, I'm good. So the value of x that would make this true is 1/35. And this would be my final answer. Right? And so the only thing that you need to check is you need to check your restriction. Right? So I need to check that 7 times 1/35 is in fact a number greater than 0. Right? And that's going to be the case because 1/5 is a positive value and a positive number is always greater than 0. Right? And so this is your process or your procedure. So let's look at another one real quick. Very similar type 1 example. And so now what we have is we have log of -m plus 2 equals 4. Now if there's no parentheses written, this plus 2 is happening after the fact. So really, with or without parentheses, the parentheses are only isolating the variable attached to log. Once you have an additional operation, that's happening differently. So this is the same thing as having a 2 plus the log of -m equals 4. So I can rewrite this using my commutative property of addition. And again, I need to isolate this logarithm, which means that in this example, I now need to subtract 2 from both sides. And again, that's not going to affect my logarithm at all. So I have log of -m equals 2. And now I can solve this by turning it into its exponential form. So again, no base written means that it's base 10. So 10 to the second power equals -m. Which means that I have 100 equals -m. Or again, I have a negative, so if I divide both sides by -1, m equals -100. Now, if I go and I check that value in my restriction, right, I need to check is negative of the value I got greater than 0. So you need to be careful because this negative is going to stay here. And if my number is negative, that really means that the opposite of a negative is a positive. And now my domain here, or my function value, is still positive. So both of these values will work as final answers, regardless of if my final variable is negative, the restriction is still positive, and that's going to be key.